Hello, this is Captain Chaudhari. In my series of videos on basic ship stability calculations, I was doing SFBM. Sometimes they ask you complex numerical. These complex numericals, their principle used is same, but the time wise they take a lot of time, so not advisable to ask the full numerical as long as you know that the student understands the basic work method which is to be used. So we will do one such question from my book. There is a ship that is 60 meters in length, 60 meters, weighing 600 tons. It has got the holds this way, which are 15 meters in length, 3 holes, and these are kind of empty spaces, or we can call them cofferdams, right? There is 150 tons of cargo level trimmed in the end holds, and there is 120 tons of cargo in the middle hold in a prism fashion. There is no slope in the athwartship direction. So this is how the loading is done. The ship can be divided in ordinates like A, B, C, D. You can actually divide it in extra number of ordinates. So E, F, G, H, I, J and K. This is how. Now in this particular question, which looks a little complicated, you are required to find out only load curve and SF curve. So to find out the load curve or SF curve, we will first find out what is the buoyancy force that is acting. As you can see, the way the vessel is weighted and the way the vessel is loaded looks like it's symmetrical about the midship, and therefore it's going to float on even keel. And let us find out therefore what is the displacement of the vessel as the cargo is loaded. So lightweight is 600 tons and the cargo is 150 here, 150 here and 120 here. So 300, this is 150, this is 150 and this is 120. So 304, 20 total cargo, and therefore it is 1020 tons as the buoyancy force or the displacement. So what is the buoyancy per unit length? That is 1020 divided by 60, so that is going to be 17, right? 17 tons per meter. We are going to find out what is the load at various points. Now load for hold number 1 and 3 can be found out like this, right? Load for hold number 1 and 3 is going to be buoyancy per unit length minus weight per unit length. And buoyancy per unit length is 17 tons per meter, and weight per unit length is going to be, because of lightweight is 600, and per meter it is going to be 600 divided by 60, that is 10, and the cargo is 150 ton, and this distance from here is 15 meters, so once again that is also 10. So we have 17 minus 20, that is minus 3 tons per meter. So the load over hold number 1 and 3 is minus 3 tons per meter. What about the cofferdams? The buoyancy is uniform, that is 17 tons per meter all over, minus lightweight is 10 tons per meter and there is no cargo there. So it is plus 7 tons per meter. Now if we consider these points, say point number D and point number H, it is the same, 7 tons per meter, because there is no cargo there. At E and G, we have done it before. When the cargo is loaded like this, the weight of the cargo at this point, or the weight per unit length at the quarter length point, which is E and G in this case, is total cargo divided by total distance. Total cargo here is 120, and the distance from here to here is 15 divided by 15. So it is 8. It is 8 here, it is 8 here, so it should be 16 here. So if I have to find out the load at E and G, it will be 17 minus 10 plus 8. That is minus 1. And that of at F, is going to be 17 minus 10 plus 16. So that is equal to minus 9. So now we are ready to draw the load curve, and we have the figures. I will write it here. Hole number 1 and 3, it is minus 3 tons per meter, and the cofferdam, it is plus 7 tons per meter. At E and G, it is minus 1, and at F, it is minus 9. So we are ready to draw the curve, as I said. And first of all, let us decide the scale. For scale, if we have a page of 16 centimeter and we want to fit 60 meter ship in 16 centimeter length, the scale should be 3.75 meter is equal to 1 centimeter. That means we can divide the page into 16 segments. So each segment represents 3.75 meters. That means 2 segments, they represent 7.5 meters, and 4 segments, they actually represent a hold. This is a cofferdam, and once again you have a hold, and then you have cofferdam, and then you have a hold. So this way it's a better thing. You might wonder, like 3.75 is not a round figure, but this is how the graph would look, and hereafter the plotting would be easier. Now I'll put the value, I'll put the alphabets here: A, B, C, D, and then E, F, G, H, and then you have I, J, and K. Now the scale of load curve. It is the maximum extension on the negative side is 9, and on the positive side it is 7. So we can take a scale like 1 ton per meter is equal to 1 centimeter. So it is 1, 2, 3, 4, 5, 6, 7 tons per meter. It is 7 here, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, 7, minus 8, minus 9. So this is a load scale. Hole number 1 and 3, it is minus 3. 1, 2, 3. Minus 3 is over here. You go this way. And over here, same thing. And in the cofferdam, it is plus 7. So I go vertically up from here. And similarly, I go up like this. At E it is minus 1, G also it is minus 1, and at F it is minus 9. So this is how your load curve is going to look I told you in my previous numerical, like as per our convention, you will find that the load curve appearing to be reverse of how you have loaded the cargo. So here you can see the cone upwards, but in a curve you will see the cone downwards. Okay, this indicates the level trimming, right? This also indicates the even load, right? Now, if we have to find out the shear force values, we will have to find out what is the area under the curve. So you can say that where the load curve runs as straight line, the shear force is going to be slant straight line. And if the shear force curve from A to C is going to be slant straight line, I better find out the value for shear force at A and C only. I can omit B because I know from A to C the shear force line is going to be straight line. So what is the area of this rectangle? So from A to C, it is 15 meters, right? 15 meters, and this is -3, right? So minus 45. So if I have to write down the shear force, which we are writing in terms of tons, at A it is 0 and at C it is -45. So -45 at C. Now what is the value at D? So it is -45 plus, now from C to D the distance is 7.5 meters, right? That is 15 by 2, and this height is 7. So 105 divided by 2, that is 52.5. 52.5 minus 45, right? That is 7.5. So you have 7.5 as the shear force value at D, right? But we also must find out what is the area of this triangle. Let us find out what is the area of this triangle. Now in this kind of situation where we can see this load curve probably is not precisely cutting the x-axis at E. Probably it is cutting at a point close to E, and let's call that point as E dash. Right? Rather than D, I'm interested in finding out what is the shear force at E dash. So for that I must find out what is this distance from here that the load curve is cutting the x-axis. So suppose this distance is x. The other side distance should be 7.5 minus x, right? So by the principle of similar triangle, can I say this height, that is 7 divided by x, that is this, should be equal to 9 divided by 7.5 minus x. We can easily calculate this. This is 52.5 minus 7x equal to 9x, that is 16x. 52.5 divided by 16 gives me 3.28. So we get the value of x as 3.28, and therefore the other side should be 4.22. So we can find out what is the area of positive area under the curve up to here, that is E dash. So it will be 7.5 plus 7 into 3.28 divided by 2. So 7 into 3.28 equals divided by 2 gives me 11.48 plus 7.5 gives me 18.98. Approximately it is 19. So this area should also be equal to 11.48, right? And the total area up to this point E dash is 19, that is a plus. Now let us find out what is the area up to F. So it will be plus 19 minus this area. Now this is 4.22 into 9 divided by 2. So 4.22 into 9 equals divided by 2 gives me 18.9. That is approximately 19. So 19 minus 19 will be equal to 0. So the shear force at mid length is equal to 0. And we also calculated this to be approximately 19. So this also should be 19. Both should be 19. So if I have to find out this point I would call G dash, right? This point I would call G dash. G dash is a point at which the load curve is intersecting the x-axis. So it will be 0 minus 19. So that is equal to minus 19. Now over here it is going to be, that means H, it is going to be minus 19 plus 11.48. 19, that gives me minus 7.52, minus 7.52. And then at I, it will be minus 7.52 plus, this is 7, and from here to here is 7.5. So 7.5 multiplied by 7, that is 52.5. This is going to give me 45, plus 45. And as you know, this area is minus 45. So at K, I'm going to get 45 plus minus 45, and that is going to be 0. So we have got the ordinates for SF, and let us plot the SF curve now. The maximum value is 45. I think we can take a scale of 5 tons equal to 1 centimeter. So starting with A is 0. At C it is minus 45. So minus 45 means straight away you come over here, right? So scale of SF is tons, and you have 0 here and you have minus 45. So we are straight away coming down like this on the shear force curve. Now the value at D is plus 7.5. So it is 5 here, plus 7.5 would be something like this. And curve is going to be a straight line curve because the load curve is horizontal straight line. The shear force curve should be slant straight line. Okay, considering the way the vessel is loaded between D and H, right? So these points D and H, I am expecting the shear force curve between D and H to be a sine curve. If you remember, we had drawn the sine curve, and the peak value of the sine curve should happen at the point of intersection of the load curve with the x-axis. Now the peak value at E dash is plus 19. So the curve is going to go like this, and the peak value will happen at the same point where the previous curve is changing direction. Now at F we have seen it is 0. So I'm drawing a sine curve. It is 0 over here, and another peak, that is minus 19, is happening at G dash. So at G dash it is minus 19. This is, so we're going to have a sine curve which has got peak value over here. The value is minus 7.5 at H. After the point H, we can see that the load curve is straight line. So shear force curve is going to be slant straight line. The next value is at I, next known value is at I, and that is plus 45. Plus 45 means over here and plus 45 means at I, I'm going to go as high as plus 45, and from there I'm going to come back to 0. So this kind of curve, problem is complex, so the examiner should ask only up to shear force. If somebody wants to find out the bending moment, the principle is same. We total up the area under the previous curve at the point under consideration and find out the value of the next curve, that is the bending moment curve. So this is the load curve and shear force curve. You can see that the load curve was straight line, and then it was slant straight line and again set of straight line. Now the bending moment curve was slant straight line till where the load curve was horizontal straight line on both the sides, and the middle hold. The middle hold was loaded in a prism fashion. So for prism fashion, the shear force curve, if you remember, is a sine curve. And we have put the peak values of the shear force curve at the same point where the previous curve is changing direction. So this is the load and SF curve for this complex numerical on SF and BM.